Yeah, today, I mean, we don't have a tutorial, so this means that I probably finish a bit faster, and then since we don't have tutorial, you can get home quite earlier today. But from next week on Thursday, we're going to have the TA for the half of the lecture. So, yeah, we ended up last time talking about the k-means clustering, right? Do you remember what was k-means clustering? What was the purpose we were doing k-means clustering, the problem that we had? So we had a bunch of points, right? Data points. And then what we had this feeling that there is a kind of pattern inside them. For instance, they can be grouped into a bunch of groups. And now we want to see how we can group them so that it makes sense, right? And then we came up with this idea of k-means clustering, right? So you remember how we do k-means clustering. So what was the model we were considering here? What does specify one specific cluster in this model? Is it a very long time since last session? I forgot everything. So do you remember what is mu1 to mu k? Remember that? So what is mu? Is the centroid, right? So centroid was the guy who was specifying the model for the learning process, right? So our model was considering like there are k different centroids. The guy, or every single point, belongs to the cluster whose centroid is closer, right? So you have one centroid here, and if you want to cluster this point, you would say I give it to the cluster whose centroid is the nearest, right? The ones which are far is not the one. So we wanted to find something that we called it the good cluster, right? Or the good centroid. And then we came up with this intuitive idea. This was the way that we did it. We said, first of all, do the cluster assignment, right? The idea was quite simple. So you have k different clusters, mu1 to mu k. And for every single point that you have, every single xn that you have inside your data set, you're going to check xn is closer to which guy, right? You're going to say xn belongs to that cluster. So the index of the cluster for xn is essentially the index of the centroid, which is closest to xn, right? So you have a bunch of points. Then among those points, what you do, every single point, you're going to just check with all the clusters. And then after doing it for all the points, then each set of points are belonging to one specific cluster, right? Now, the next thing that we do is that we're going to update the centroid of the cluster. So we initially start with some random centroids, right? And then we would say, okay, now, if this is really the centroid of the cluster, it should be at the center of that cluster, right? Everything is somehow distributed around it. If this is not the case, so we update it to that one. Basically, it means that we're going to get every point inside cluster K, right? Every single xn that is inside CK. And then we average them out, right? When you average a couple of points, you basically take the point at the center, right? And then that guy is the point, like the sum of those x's inside the cluster divided by the number of points you have inside the cluster. That is the averaging. You update the centroid like that. And you keep on going like this, right? You keep on just updating like this till this algorithm is going to converge. It means that the centroids are not getting updated anymore, right? Everybody recaps, right? Everybody recalls what we did last time? Yeah? Okay, cool. So that was the idea of k-means clustering. And what I told you last time was that k-means clustering is actually a good algorithm. Or in other words, the way that this k-means clustering is finding the centroids, this is a kind of good way, or a good choice of centroids are being given by this algorithm. But I did not tell you how I define being good, right? And this is what we want to do today, right? We want to see how we can formulate the problem of clustering concretely, and then try to solve it, and you're going to see that we're going to get back to k-means clustering. Okay? Cool. So let's start with the model that we had before. This is the model that we had. We called it k-centroid model. So what does it do? Basically, it assumes this is the one we just discussed right now. So you have k different centroids, mu1 to mu k. Then the clustering is simply done in this form, right? X is just compared to all the centroids, and the one which is closest is specifying the cluster, right? This is the k-centroid model, and now the learning algorithm that we have is going to take data points, right? And then it's going to specify the model. And inside this model, we talked about this last time, the only parameters that you have and you can play with are the centroids, right? So because the model, the k-centroid model, is somehow assumed by you. You might say that, well, I don't think this is a good idea to just cluster every point in the space by checking its distance to a centroid. Well, that is your choice. But if you think this is a kind of feasible model, then you have a bunch of parameters inside this model, those mu's, right? And then the learning algorithm is what it basically does. It looks at your data set, all the samples that you have, and then out of that it tries to find out what is the right choice of mu's, the centroids, right? Yes?
Depending on your initial choice of centroids, could that dictate the final? Or?
Yes, that could.
Okay.
Yeah, we're going to talk about this. This is not, I mean, k-means clustering is not solving the optimal solution. It's just giving you a good solution. Yeah, it's just a local optimum. Yeah. Everybody's cool, right? Everybody remembers. This is the k-centroid model, and this is the learning algorithm. The k-means clustering algorithm that we had last time is actually a learning algorithm, right? It takes the points that you have inside your data set, right? Look at it here. Just it looks into the points that you have inside your data set. So it gets the data set. It does these two steps iteratively. Finally, it converges to a bunch of mu's, right? So it takes the data set, returns you the centroids, right? The parameters that you have. So it's basically a learning algorithm. Now, I claim that this is actually a good learning algorithm. It means that the centroid that it's finding are a good set of centroids. And you might ask me how you can define such a thing. Well, this is the way that we're going to do, and hopefully this is a good start for doing the next step in the lecture. So, the thing that I'm going to do, I try to formulate what I want, or intuitively I feel like is the right pattern inside the data. I try to formulate it with a bit of concrete formulation. So what do? Let's say I have this data set D, and this data set has a bunch of points, right? N different points. The thing that I want to do, for example, I assume that I have k clusters. I want to put them into k clusters, right? I want to group them into k different clusters. So this is the task that I want to do. Now, the thing that I can do, I can define a coefficient for every single point inside my data set. And that coefficient is essentially telling me that to which cluster this point should be assigned. So this is what we call it, assignment coefficient or assigning coefficient. But I mean, it's not really a general word. I think Bishop calls it assign coefficient, but I just simply call it a weight. Now, what is the property of this guy? This simply, if it is 1 for one particular n and k, this means that my point xn belongs to cluster k, right? So I want to assign point n to cluster k, right? But if it is 0, it simply means that x does not belong to that cluster, right? So if you have one specific x, one specific data point, right? Now, this guy has k different coefficients like this, right? How many of them are 1? Just one of them, right? How many of them are 0? K minus 1, right? Everybody's clear? You get the idea? Now, if that's the case, now let's see what kind of properties this guy has. Now, say that I do something like this. So I get these coefficients. I focus on one single point. I sum up all the coefficients on k, the index of the cluster. What should be this summation? It should be? That's right. Should be 1, right? Right? it should be 1. Because one of them is 1, the cluster that the point belongs to, right? Everywhere else, it's 0. Everybody's cool? Yeah? Now, let's do another thing. Now, let's fix K, the cluster, right? So I'm going to fix K, the cluster that I have. And now, I am going to sum up this coefficient over n. What should be this guy? I mean, it's not 1, definitely. It's not just an integer. It's representing something. It's not K. No. Number of points in the cluster, exactly. This is going to be the number of points inside the cluster. Everybody sees that? Right? If I fix the cluster, right? And then I have n different points, now I see, does it belong? If it belongs to this cluster, the coefficient is 1, right? I'm going to have 1 here. The next one, does it belong? No, so the coefficient is 0. This one belongs? Yes, it's 1, and so on, right? If I add up all of those 1s and 0s, I am basically counting the number of points inside that cluster, right? Everybody sees that? Everybody's cool? Okay, so if you see this, then basically what we did before in the cluster assignment in our k-means clustering algorithm, we can write it down in that form. We can write it down in terms of these coefficients R, the assigning coefficients, as well. How we can do that? I mean, basically what it does, it is start for every single point n, and then for every single point you need k different assignments, right? And those assignments are either 1 or 0, right? It's going to tell you which cluster it belongs to, right? So what does this algorithm do? The algorithm that we wrote before is basically looking into all centroids, and the one who is closest to your data point, it's going to give the coefficient or set the coefficient to be 1. For anyone else, it sets it 0, right? Everybody's cool? Everybody's clear? Questions? So what it does, it looks at the data set, the centroids that you have, and then for every single point, it checks which guy is closer, right? It's going to give you back a bunch of coefficients. Those coefficients are 1 and 0. When it's 1, it means that that point belongs to that specific cluster. If it's 0, it does not belong to that, right? Everybody's cool? Yeah? Great. So that is what we did for cluster assigning. And then the next thing is the update of the centroids. So how did we update the centroids? Well, when we want to update the centroid in k-means clustering, we go inside each cluster. We just average everybody inside the cluster, right? So now I show you the expression. You tell me whether it's fitting what we said before or not in terms of these new coefficients R. I write it down in this form. Does it make sense? First, let's look at the denominator. What is denominator? I am fixing the cluster K, right? And then I'm adding up over n. What happens? Number of points inside that cluster. So this denominator is basically size of cluster K, right? So this is size of cluster K. What's going to happen inside the denominator? I'm looking at every single point, right? Then I multiply it to its coefficients, R and K. If point n belongs to cluster K, what would be this R? 1. If it does not belong, what would it be? 0. So what's going to happen at the end of the day? Those guys who belong going to show up with coefficient 1. Those who do not belong going to show up with coefficient 0. So it means that they actually do not show up, right? So the denominator is sum of all the points in the cluster, right? So denominator is all the points in the cluster added up, right? Denominator is size of the cluster, right? So that expression is the average of the points inside the cluster, right? So it's the same thing. I have not done any magic, nothing. Just represented what we had in the intuitive algorithm in terms of R, right? And as you can see here now, I don't have any set C anymore, right? Clear? So set has gone. Instead of that, I am representing it with a bunch of coefficients, 0 and 1. Those coefficients are telling me which guy is assigned to which cluster, right? Everybody's cool, right? So I can represent the algorithm that I had now in terms of this coefficient R is just the change of notation, nothing else, right? Now, this notation, however, is going to help me to reformulate my problem. Now, our algorithm, the k-means clustering, what it does, it basically just looks at the centroids, the initial centroids that you start. It's going to compute a bunch of coefficients, 1 and 0. It's going to say which guy belongs to which one, right? And then after having these R, you can put these R's into that second algorithm, and then you update your centroids, right? And you keep on going like this. This is basically k-means clustering, right? Now, I told you that this is a good algorithm, or these are a bunch of good centroids. And now you might ask me that how you can say, well, let's try to define what is good centroid. Now, if I have a bunch of points in the space, or in the plane, I have a bunch of points. And now I want to find, like the example we had last time. So if I have something like this, I got my data set, and my data set is two-dimensional, and I got a bunch of points like this. So the points that are happening are like this, right? So intuitively, you see that these guys are probably in one cluster. These guys are probably in another cluster, right? This is, if I tell you I want 2 clusters, you're going to do that, right? If I tell you more, probably you zoom in more to see whether you can distinguish between them again, right? Now, if you want to choose 2 clusters, where would you put them? I mean, center was the idea, right? Center was the idea that we had, and it made sense. But why it should be centered, right? I do know this guy has a centroid, right? But why should it be centered, right? Anyone has any question? Any idea? Yeah. To what? All of the guys, right, right. So if I am thinking only about this single point, right? Putting the centroid here or putting it here, it does not matter, right? It's the same distance here and here, right? It's the same distance. But when I have a bunch of other points, like I have some guys around it, right? The thing that I would do, I would put it in a point which gives me shortest distance to this one, and to this one, right? Everybody's clear? So probably what we do is that we think of the points and we say every point belongs to a cluster, and every single point, every point to its corresponding cluster should be as close as possible, right? This is a way that I can define goodness, kind of being well in my pattern, right? Because I am thinking in terms of distance, right? I am using a centroid model. This means that what specify the cluster is distance from the centroid, right? And now the thing that would make this model better is that this distance is smaller and smaller, right? For instance, if you collect 100 samples, okay, and all the samples happen at the same point, 50 of them here, 50 of them here, right? Then you obviously would say, okay, I have 2 clusters, both of them exactly happening here on those points, right? Why you say exactly those points? Why you don't say here, right? Because you would say when all the points are here, there is no point that I put the centroid anywhere else, right? The centroid is exactly here, where the distance from all the points inside the cluster is 0, right? I don't need to make it more than 0, right? The same thing here. Everybody's clear? So probably the best idea that I can define a good centroid is that I think of the centroids being close to their corresponding points inside the cluster, right? Okay, let's do it together. Now let me just write down this formulation. Now everybody looks at this. I I am defining one function, this j, okay? And this function j, this is an objective function I want to design. Somehow this is going to describe what is good clustering with my model, okay? Now, first look at this term here, r and k times distance between xn and mu k. What does it represent? Think about that. If I think about one single point xn, okay? Now, xn could be in one of the k clusters, right? Now, if it belongs to cluster k, what should be this r term? 1, right? And that is going to give me the distance between xn and its own centroid, right? If xn does not belong to cluster k, what would be that r? 0, right? And then what would be that term? 0 simply, right? So this first term, this is going to tell you this is always 0 unless this point xn is really inside the cluster k, right? And when this guy is inside the cluster k, this term is simply telling you how far your point is from the corresponding centroid, right? The centroid of its own cluster. Everybody's cool? You see that? Now, the next thing that I want to do, I am going to add it up over n. So I'm going to aggregate this distance over all the samples that I have inside my data set. Now, what am I doing? So back to this guy, if this is point xn, this term is going to only show up something non-zero when I am thinking about its own cluster, right? So for point 1, this guy is giving the distance to its own cluster, and anywhere else it's 0, right? For point 2, it's again giving the distance of point 2 from its own cluster, right? And so on towards the end. Now, if I add them up all, what's going to happen? Is the aggregation of the distances for every single point from its own cluster, not everybody, right? Just its own cluster, right? So you assume that x belongs to cluster 3, and then you only care about the distance between x and centroid of cluster 3, right? Everybody's clear? So if I want to do it on this graph here, what do? I compute this distance, add it up to this distance, add it up to this distance, right? And this is cluster k equal by 1. Here the cluster is k equal by 2, right? But if k equals by 1 here in this expression, you see that I am not yet doing anything on k, right? Everybody sees that? So I'm not doing anything on k, so what I'm doing here, I'm just adding up those guys, if I set k equal by 1, the distance of those guys which are in cluster 1, cluster k, from their own centroid, right? Everybody's clear? So if here, maybe those who sit far away cannot see it, so maybe with a few points, 1 point, 2 point, 3 point, 4 point, and here this guy is mu 2, this guy is mu 1. If I set k equal by 1, then r point 1, so say this is x1, x2, x3, x4, then n is going to run from 1 to 4, and x1 from mu1, it is inside the cluster, so it's going to show up. x2 from this guy is going to show up, but x3 does not belong to this cluster. You don't compute this distance anymore, right? You only compute the guys who are inside this cluster. Everybody sees that, right? So this guy is now sum of the distances of every single point that belongs to cluster K, right? Yep, go ahead.
Why don't we square the distance?
Well, the main reason is that that's going to be numerically or computationally easier to optimize at the end of the day. I mean, you can define it another way, but a better answer is that actually we are somehow, I'm going to mention it very briefly at the end of this lecture, and then next week we're going to see it, but you're somehow assuming that your data is distributed Gaussian. And if you assume that, then this is the energy, and this should be the square. Like the expression in Gaussian distribution, the exponent is always squared, right? Yeah, that's the main reason. But we're going to talk about it later more. Yeah. So everybody sees what I'm doing here, right? Okay, so adding it up like this, and then the next thing that I'm going to do, I'm going to aggregate over all clusters, right? So I guess you get what I'm doing now, right? So this one was the sum of distances for points inside one cluster. Now I compute sum of distances here. Then I go for the next k. I compute sum of distances here. Now I'm going to add them up, right? So this last term is adding up the distance of every single point that you have in your data set from its own centroid, right? Everybody's cool? Now, does it make sense as a kind of objective to make it small? When this guy is 0, what's going to happen? Every point inside every cluster is exactly lying on the centroid of that cluster, right? Right? So you could have k different clusters, and everybody inside that cluster is actually lying exactly on the centroid of the cluster, right? Everybody's cool? You see that? Yeah? And if it is very large, this means that every point is far away from its own centroid, right? So this means that this is not a very good centroid, right? Now, one last thing that I might do is that I might just divide it by n, so I actually average it over the number of points that I have, right? If you want to think numerically, why you do it, I don't want to have a large number. Yeah, that makes sense. Another thing is that I want to know somehow per each point what is the average distance to the centroid, right? So in average, every single point, if I randomly choose, how far it is from its own centroid, right? And if that guy is very small, then my clustering is working fine. If that is very large, this means that every random point that you choose is very far away from its own cluster. That does not make sense. This is not a good clustering, right? Everybody's clear? Cool, great. So now that you have this one, now if I want to formulate the optimal clustering, I can say that this objective is something that is describing the pattern that I want. I want every point to be very close to its own centroid of the cluster. So the thing that I might do is that I get this objective term and I try to minimize it, right? Yeah.
I might be jumping ahead, but if you increase the number of centroids, won't that make it easier to reduce?
Definitely. If you have as much centroids as the samples you have, then this objective could easily be 0.
Right, but let's say you don't go to the number of points, you just increase it. Won't you always decrease?
Yes, yeah.
So
I'm going to mention it later, yeah. Yeah, but yes, that's correct, because your model gets more complex.
So how do you know when to?
That is the matter of design, right? I'm going to give you one concrete example of image clustering, and then you're going to see when it makes sense. Or what is the choice? It's actually a design choice. Okay, now everybody feels fine about this kind of formulation. So what is the clustering that I want to do, right? So here in this optimization that I have, what are the variables that I want to optimize? The signings are choices of R, right? I have n times k different of them, right? For every single point, I have k different coefficients. One of them is 1. Rest of them are 0, right? And then I have n different points, right? So it's a big matrix of different coefficients. Every row is just having one single one, remaining 0, right? So this is one variable that I can play with. Another variable that I can play with is my centroid, right? And now I want to just optimize this guy, right? I want to find the point or the choice of R and mu which makes this objective minimum. Then I feel like my clustering is working fine. Questions? No question? Okay, great. So if you got no question, then first of all, anyone has experience with optimization? Anyone has any feeling what kind of optimization is that? Can you solve it easily or no? Why? I don't expect you to know, just out of curiosity if anyone has an idea. Is it a simple optimization or no? Just do a random guess. Yes or no, randomly? Yes or no? No, it should not be, right? If it was like, I would end up the lecture right now. It's not a very simple optimization. Do you know why? R and mu depend on each other. I mean, they both together are not expressing a convex term. That is correct. And because of that, the problem is non-convex. But there is also one more challenging constraint to the problem. R should be binary, right? 0, 1. It's integer programming, right? Like you cannot choose any choice of R, right? So you're dealing with integer values. It's a bit challenging to solve it. Not too challenging, but it's rather a bit challenging. And long story short, a closed form solution to this one you cannot find. You cannot say, I mean, this R and mu choice is the optimal choice. Now, what do people do when they want to solve such a problem? There is one trick that we call it alternating optimization. So what we do, we'll look at the variables that we have in our problem. Then we would say, for example, in this expression, if I fix R, right, then it's not a very hard problem to optimize it in terms of mu, right? Or if I fix mu, it's not a hard problem to optimize it in terms of R. Now, if this is the case, then I can solve the problem in this way. I can initiate everything with a bunch of choices for mu, right? So I say mu1 to mu k star, and then this guy is fixed, so I'm going to fix mu to be mu star, and then I would say, okay, I play dumb. I treat mu as it is constant, right? And then I optimize the function in terms of R, right? Now, once you've optimized it, you're going to get a bunch of choices for R, right? These choices are optimal when mu is the choice you had, right? But that choice of mu is not necessarily correct, right? The next thing that you're going to do, you're going to say, okay, now I'm going to play down the other side. So I would fix R to be fixed to what I computed in the last step, right? And then now I try to optimize it in terms of mu, right? Now you're going to get a bunch of new choices for mu. Now you want to see whether you should stop or not. You're going to get back to line 3. You put the new choices of mu there, and you optimize R. If R is the same thing, then you stop. If R is changing, then you repeat, right? And you keep on going till your function, algorithm stops. Like nothing changes, right? Everybody's clear? Now, if you want to think in terms of function optimization, it's like you have a two-dimensional function, and then you would say, okay, I'm going to just cut the surface and look at the one-dimensional axis, right? On that cut that I have, I'm going to see where is the best choice of the other variable, and then I stay there, and I cut again the other direction, and again I keep on optimizing, right? Now, if your function has a global optimum, a single one, which means that it is a convex, then doing this, you're going to end up there, right? That's okay. But the problem is that usually this function is not that one, right? And it's going to look like this, right? And it might be that you do not end up with the best choice of R and mu, but one of them which is locally optimum, right? This is why I'm showing it by a star here, and this star is different from this star, and I'm not sure if you can see the difference because I cannot see it on the slides right now. Yeah, but this star is different from that star. But whatever you get, okay, here is a bit more clear. So these guys are different from these ones, but these are approximation of that guys, right? And this is what you have. I mean, you can do nothing about that. Like, you cannot beat the computation ever. Everybody's clear? Okay, now I want to optimize the objective. Let me do this and see what do I end up with, okay? Let me start with the first one. So in the first one, I want to fix mu. I'm going to fix the centroids, right? And then I want to optimize in terms of those coefficients R, right? Once again, what is Rnk? It's 1 when xn belongs to cluster k. It's 0 when xn does not belong to that cluster, right? Just remember, right? Okay, now let's go ahead, write down this objective. This is the objective that I have. Okay, this is going to be the sum of all these terms, right? Now, what I am going to, this is xn, a difference from the cluster k, right? When xn is inside the cluster, so it means that I'm computing the difference of every point from its own cluster. Now, the next thing that I'm going to do, I'm going to keep n as the summation, and I'm going to expand the summation in terms of k. Everybody's cool? So I have done nothing. The difference between this one and this one is that I am just opening up the first summation in terms of k. Okay? Look at this one. N is fixed here, right? And then Rn1. So here is Rnk. So if I sum up over k, it's going to be Rn1, xn mu1, right? Rn2, xn mu2, and so on. Rn capital K, xn mu k, right? Everybody's clear? Everybody sees that? Yeah? Okay. Now, look at this term, okay? And I am doing it like I have lots of r's, right? Right now, I just want, forget about all of this summation here because it's not going to impact. I just want to minimize this expression inside the brackets. What is the best choice of r? Let's think about it first, right? Rnk. Can it be any number? No. It can be 1 for one of the k's, right? It should be 0 everywhere else, right? So whatever I choose, if I, for example, set Rn1 to be 1, what can happen to Rn2, 3, so on? It's going to be 0, right? And what's going to be this summation, this bracket? It's going to be the first norm, right? xn mu1, right? Correct? If I set Rn2 equals to 1, then what's going to happen to the others? 0. What comes out of the bracket? Distance between xn and mu, 2, right? Everybody sees that? So the choices that I have is that I pick the first term, or I pick the second term, or I pick the last term. Which term do you choose? You want to minimize. Everybody's following? Yes? Everybody sees what your friend said? Yeah? Once again, this R and K, this can be 1 for a single K, right? For any other K, it should be 0, because your X belongs only to one cluster, right? Everybody's clear, right? Now, this means that when I open up this summation, if this first R is 1, any other R is 0, right? And this whole summation going to be the first distance, right? If I set Rn2, the last R to be 1, then this last guy coming out, everybody else going to disappear because those are 0, right? Now, if I want to find the choice of R, which is going to maximize minimize this expression, what should I do? I do know that any choice of R is going to pick one of these distances, right? So if I want to minimize, I'm going to choose the one which has minimum distance, right? Everybody's clear? You get what I'm saying? You see it or not? Yeah?
Oh, I just going to ask why though. I mean, I understand why you picked the one with the small distance, but
yep.
Why are we doing this?
Because we want to minimize this whole objective, which we defined in terms of R.
But I mean, if you just pick the one that has a small distance, what does that signify at the end? What does that mean at the end?
That means that you're assigning the point to the cluster which is corresponding to the minimum risk, right? Minimum risk that you could have. The risk that you define, right? Okay. Yeah? Everybody's clear? So does it make sense? So this is going to be the solution of this optimization problem. And everybody sees that, right? So the solution to this optimization is that you pick the guy which has the minimum distance, right? So among all of the centroids, you are going to select the one, so K is going to be the one which has the minimum distance from xn, right? Do you remember this? Did we do it before? That was the cluster assignment algorithm we had, right? So this is the same thing as we had before, right? So basically this cluster assignment algorithm that we had, it looks at the centroids that you have, and it tries to find the assignment coefficients, R's, that are giving you the minimum risk. Everybody's cool? Questions? No question? Okay, great. So if you got no question, now let me try to solve the second problem. So we initially fixed mu. We optimize everything in terms of R, right? So we did the assignments, R are nouns. So you do know which point belongs to which cluster, right? Now that you fix this, it means that you fix R. Now you want to solve this optimization problem, and this time you want to optimize it in terms of mu, the centroids, right? R is fixed, you want to solve it in terms of centroids, right? So let's do it together again. Let's open up the term. So I'm just replacing the term, and this time what I'm going to do, I'm going to keep the K out, and I'm going to expand the term in terms of the summation in terms of n. Now, look at this guy. If I compute the summation in terms of n, I think we did it before. What does it represent? So this R, n, and k is only one for those n's which belong to cluster K, right? So I can simply say that this summation is this guy, right? Is the summation of the distance of xn from centroid K that belong to cluster K, right? Everybody's clear? Now again, I am doing it for every single mu, so let's focus on one single mu, okay? One single mu. You don't care about this summation over K, right? You want to minimize this expression inside the bracket. Now, how do you do that? You have a bunch of points inside a cluster, and you want to find a point inside this cluster which is in the minimum distance or aggregated distance from all the points inside the cluster. What is that point? The center of the point, right? If you have a surface and you have specific mass points, and then you want to find the central mass of that surface, what do? You average the masses, right? It's the same thing, right? So if I'm pretty sure that everybody could intuitively at least see it, but if you don't see it, just go ahead, take the derivative, set it to be 0, and then you're going to see that mu, the optimal mu, is the average of x's. Everybody's cool? Questions? So the optimal solution for every single centroid is just the average of the points inside the cluster. Does it remind you of something specific we had before? It was the update we do in k-means clustering again, right? So in the k-means clustering, we had this update. This was the centroid update. And basically, after doing the assignment, we just look at all the points inside the cluster. We take the center of those points, right? The average of those points. And basically what you're doing, you're trying to marginally optimize your risk in that case, right? Questions? No question? Everybody's cool? Great. So if you got no question, then we had this risk minimization algorithm. In the risk minimization, we say we start with a bunch of mu. Then we optimize in terms of R. Once we found the optimal R, then we fix R and optimize in terms of mu. And we keep on going like that, right? If I write down that again, this means that when I fix mu, then after that I'm going to just optimize R. It means that I'm going to use cluster assignment, right? Because cluster assignment is optimizing the assignment coefficients. And as we saw, the next optimization is going to be solved by centroid update algorithm we had last session, right? So This means that this risk minimization is nothing but, have you seen this algorithm before? It's k-means clustering, right? You fix the centroids randomly. While the centroids are changing, you just give every point inside your data set to a cluster, and you do it by just finding the closest cluster. And after that, you update by averaging the points inside the cluster, right? So that guy is basically, this guy is basically k-means clustering. So k-means clustering was not simply an intuitive algorithm, even though it makes sense intuitively for you what we did, right? But you basically define a risk function, and this risk function somehow helps you understand what you want. Then you try to minimize this risk function, and then out of minimizing it, you end up with one algorithm. And it turns out that k-means clustering is actually a solution to that problem. Questions? Yes?
Is this only for circular clusters?
Sorry?
Is this only for circular clusters?
What do you mean by, yes, yes. You mean the, like they have the variance, right? Like is the covariance matrix is identity, right? But we're going to talk about it later. You mean that like it's not an ellipse, right?
Yeah,
an oval. Yeah, well, I get it. Yeah, yes, it's a circular cluster right now. But we can do it actually non-circular. Then we're going to see it after you see the density learning. Questions? No question? Everybody's cool? Yeah.
I'm unsure on why is it not necessarily an optimal problem if we don't alternate.
Oh, if you don't alternate, yeah, you definitely can. I mean, like you do it once, right? You mean? You just optimize R and then mu and that's it?
Yeah, like just do the minimize, like try to minimize the risk without fixing either.
Oh, you cannot solve the problem. Computationally, it's hard for you. Like the expression that you have for this, this expression here is not a convex function in terms of all the variables, right? If I fix R, then this is a sum of its quadratic terms, so it's convex. If I fix mu, it's just a linear programming, and then with a very nice constraint, linear constraint that you can again solve. But if you want to solve at the same time for both of them, it's not. Yeah.
Does the order of fixing mu or R matter?
I mean, like theoretically, like it's hard to say. Theoretically, it should not matter. I mean, if you start with any of them, then you're going to end up with a local optimum, but you do not necessarily end up with the same local optimum. And of course, I mean, in an extremely non-convex or extremely non-convex situation, you could have it that if you start with different random points, then you end up with different solutions, and this is some imperfection that you have.
So why don't we recursively do like fix mu of R?
That one is because the problem for mu is better defined. I mean, first of all, generating randomly centroids and assigning, this is easier or more intuitive as compared to the other way around. And the second thing is that like solving the problem for R is more challenging. This is why we don't want to randomly start with that one. Like it's going to give us a bit of more stability, just this. But if you do it the other way around, yeah, like randomly you generate assignments, and then you do the update and you keep on going, it should work fine. But I cannot guarantee that in a weird situation you end up with the same clustering. No. So, any questions? So one point, I think I need about half an hour. Now, should I keep on going and then we finish earlier, or do you want a break? Huh? I keep on going? Like, in a very democratic way, I keep on going? Yeah, okay. Yes, okay. So, great. So, one thing regarding this risk that we have defined, this is going to give you a better idea. I mean, you're gradually going to see it after doing multiple learning tasks, that you always need to have a risk for your learning design. learning algorithm design. And when you have risk, you can eventually have some metric by which you can evaluate the performance of your trained model or learned pattern. For example, here, if you, for instance, do k-means clustering, well, I told you that you can just keep alternating between the two algorithms until you converge, right? And this means that nothing is going to change. But the better thing that we could say is that you can start computing the risk term, right? So initially in the very first, or maybe 0 here, when you have not done any assignment or you have not done any step of optimization, the thing is that you have random, for example, assignments, random centroids, right? And the choices are extremely bad because risk is significantly high, right? Now you do one step of k-means clustering. It means that you just assign to the centroids and then you update the centroids, right? And then after doing this, you are going to drop significantly in terms of the risk, right? And as you keep on going, as you do more and more iterations, this guy is going to drop lower and lower, right? And then at some point, it's going to just saturate, get into a plateau, and then this simply means that your algorithm has converged, right? Cool? Great. So now, let me just give you one concrete example. This is going to make it a bit more interesting to listen to k-means clustering. So look at this image, and I want to do a sort of clustering in this one. And what I want to do is that this is an RGB image, right? And you do know what is an RGB image, right? It has red, green, blue channel, right? Every single channel is a matrix of pixels, right? Clear? Right? So every single pixel has 3 components. The level of intensity for red, level of intensity for green, level of intensity for blue, right? Now, if you have this image, and I don't know exactly, this is taken from Bishop's book, but I don't know exactly what is the resolution, but say the resolution is 100 by 100, okay? It means that you have 100 pixels on width, 100 pixels on the height, and then you have in total 10,000 different pixels, right? So this image has 10,000 different small pieces, right? And every single small piece is one vector, right? Clear? Everybody's cool? Now, what I'm going to do, I'm going to say that these 10,000 points, okay, they are 10,000 different samples, right? Every single sample is a point inside 3-dimensional space, right? The RGB vector, right? And this RGB pixel is actually presenting the intensity or the color of one of these pixels inside this image. Now, what I want to do, I want to cluster them. For example, I want to say there are majorly 3 clusters in this among these 10,000. I mean, I have 10,000 samples, 10,000 pixel vectors inside my data set. And they belong to 3 different clusters, right? A group of them, which are probably very high in intensity in all the colors, a group of them which are in the middle ground, and a group of them which are extremely light, right? For example, I want to do that, right? Everybody's clear what I'm doing, right? So I'm going to do k-means clustering on this guy, right? And once I am over with k-means clustering, I am going to show every single point inside the cluster with its centroid. It means that if, I don't know, one of the pixels here for the red one belongs to cluster 1, I am not putting the red pixel anymore. I am going to put the centroid of the cluster that this red pixel belongs to. Everybody's clear? You get it? What I'm doing? So if you do that, then you can start doing it first by k equal by 10, right? And when you do this, you're going to see this one, right? Now, on this image, when you look at this image, every single pixel that you have belongs to one of the 10 possible centroids, right? So you have only 10 possible choices of the pixel, right? So every single pixel belongs to one of those 10 vectors, which are the centroids you found by k-means clustering, right? Now, if I keep on going, for example, if I do it for k equal by 3, then this is going to look like this, right? So one of the clusters is actually representing the light pixels, right? This is the one which is somehow white or maybe very creamy ice cream, vanilla ice cream color. I don't know what is that. Then you have a brownish color, and then you have a black color almost, right? These are the three different clusters. So you have three different clusters, and all the pixels, each pixel belongs to one of them, right? And you're showing the average one, right? And if you do it for 2, then this is now only 2 ones, right? And now, have you ever seen such a thing in your life? Yeah, and they are doing, I mean, they used to do it by k-means clustering, right? Okay? Everybody's cool? If you want, you can try it at home. Just download this image, import it to Python, take it as a tensor, and then you do that. I mean, PyTorch has its own images, so you don't need to really import this one. Sorry?
Like, right now you're decreasing the k from 10 to 2 so the picture gets less and less detailed, right?
Right, right.
If you go up.
Yeah, it's going to get better. It's going to get better.
Like, is there like a cap? Is it going to get worse
Right.
by going better? Like, say you like,
no, it cannot. It
okay.
cannot.
It's not
Because if you have as much clusters, I mean, this guy, this is the original one, right? How many clusters you have here? You have as much as pixel that you have. You have 10,000 clusters, right?
Yeah.
Because every single point is its own cluster, right? Its own centroid.
So k max
is 10,000, for example, if you have 100 by 100 image, right? Okay. And then as you decrease, the quality is going to go down, of course, because you are just restricting pixels around each other to just be represented with one centroid, right? So it definitely go down. Questions? Everybody's cool? Now, one thing that you might notice here is that the more k you have, the better the quality was in the image, right? And then you can simply formulate it in this form. You could say that the objective that you have is going to somehow be better and better if you have higher number of clusters. That makes sense. I mean, if you have more centroids, you can group your points better such that the total aggregated distance is smaller, right? So the formulation makes sense to what you see as a pattern inside your image. And this is why this formulation is actually a kind of nice formulation for finding the clustering algorithm. Everybody's cool? Questions? Now, back to the question your friend asked at the very beginning of the course, this choice of k, this is a design choice, right? If you really want this guy, k2 is enough, right? But if you want to have this one, you need to have at least k10, right? So it depends what you want to do, right? Yeah? Are you trying to, for example, make it anonymous and just keeping it to now whether it's a child or not? Then probably you want 2 or 3. But if you want to make it completely feasible, then probably you need higher, right? Okay, cool. Now, yes, go ahead.
Can you define a hyperparameter, like what you described, a hyperparameter?
Hyperparameter is actually we're going to talk about it more when we get a bit into neural networks, but hyperparameter is something that you fix in order to describe your model, right? If you want to say k-means like you want to do, like you have a k-centroid model, right? You need to fix k first. For example, you say I have 3 clusters. Then this means that I have 3 centroids. Now you can write down the model, right? I have mu1, mu2, mu3, right? But if you just simply say k, what is k, right? You cannot write it down. So that is something that you specify before ahead, right? And then your model is specified. Then you just train it, meaning that you find mu. But we are not completely yet there. I mean, we get more there when we get into supervised learning. But for the moment, just, yeah, hyperparameter means something that you fix, right, before ahead. Questions? No questions? OK. Now, one question that you might ask me is that, does this k-means clustering always converge? It means that if I start with random centroids and I keep on iterating, do I end up with algorithm stopping? Yes, that is going to happen. And you can simply prove it. If you want to take a look at the proof, just check McKay's book. He has the proof there. But there is one key point here. And the point is that you do not necessarily end up with what you want. This is the key point. Convergence does not mean that you end up with what you think is the right clustering. Okay? Convergence means that your algorithm is going to run and then it stops, right? But maybe it assigns every point to a cluster, and that cluster does not make sense to you. Okay? So look at this one. This is one example from McKay's book. And you have this data. These are the samples from your data set. What are the clusters that you would say? You want to have two clusters. What would be the clusters? The left one and the right one, right? Probably these are the clusters, right? But if you start with some random initial points and two clusters, then you're going to see something like this. So I did not take the one which has been shown after the complete convergence, but the thing that is going to happen is that there are a bunch of points here and a bunch of points here that they end up belonging to the same cluster, right? This does not make sense to you, does it? So you wanted that left guys be one cluster, right guys being one cluster, right? But you don't get it. And if you want, just go ahead, do this one, but your points should be extremely narrow, right? They should not concentrate around the center, around the circle, sorry. It should be like an oval shape area, right? And if you do that and then you randomly choose two start points, then most probably you're going to end up with a very bad clustering. Like a bunch of points here, and here are going to be one cluster, a bunch of points at the top going to be another cluster, right? Everybody sees the point that I'm talking about? Now, the question here is why that is happening, and hopefully next week it's going to get very clear for you why that is happening. Because actually what you're doing with k-means clustering, you're assuming a kind of unit covariance distribution for your data, and Gaussian distribution for your data. And since you are thinking of that, your model is somehow imposing this structure on the data, that everything should be around a very uniform bell, and it's very symmetric bell, which is not the case here, right? Here your bells are not symmetric, right? So the areas are very stretched on the y-axis, but very squeezed on the x-axis, right? They are not on that one. But don't worry, we're gonna get there when we study density learning. Now, one thing that people started to resolve this issue was the idea of soft clustering. So I'm not going to go into too much details as we did with the k-means clustering. I just want to give you the algorithm. If you want to see the details, we can check McKay's book. But I want to give you the idea how people do it. So the idea was that when we formulated the risk, we just wrote down those assignments, right? And those assignments, we said that they are going to add up to 1 when you add it up over the clusters, right? Every single point belongs to one single cluster, right? Correct? And then if I say point n belonging to the first cluster plus point n belonging to the second cluster and so on, this is going to be 0 everywhere but 1 at one single one, and that is adding up to 1, right? Now people said, okay, we are saying that we need to find these coefficients which add up to 1. They are all either 0 or 1, right? What's going to happen if instead of being 0 or 1, I say this is any real number between 0 and 1? What's going to happen, right? What does it mean? If you have k different numbers, right, and every single of them is between 0 and 1, and they add up to 1, what do they represent? A probability distribution, right? Correct? So people said, yeah, maybe we can look at this as a probabilistic thing, right? We could say xn has k different choices of assignment. Each of them is a number between 0 and 1. And maybe that is representing the chance of xn belonging to each of the clusters, right? Maybe that is a better idea, because it's changing a binary integer problem into a nice, well-defined linear programming problem, right? That is much easier to solve, right? So people thought of this probabilistic assignment, and the probabilistic assignment simply means that you have still these assignment coefficients, but they are not 0 or 1, they are between 0 and 1, and they add up to 1 when you add them up over the clusters. This simply represents the chance of every single point belonging to one of the clusters. And of course, if you have 1 point, it at the end of the day belongs to one of the clusters, right? When you add it up over all of them, it's going to be 1, right? So they did that one, and they said, okay, maybe we can write down the risk term once again as before, but this time we think of those r's to be the probabilities, right? Let's see what's going to happen. Okay, this was the risk term that we had, right? Distance x to the cluster k, and then I added up over all n's and k's, so every single point from its own cluster when r is between 0 and 1, right? Sorry, r is either 0 or 1, okay? Now, let me just do it on the board for you so that you see this. I want to do it quickly. Oh, no, sorry. Okay. Let's say I have this particular point x, right? And I don't know which cluster this point belongs to, okay? I have k different clusters. This is cluster 1. This is cluster 2, for example. Let's say k equals by 2, so keep everything simple. K equals by 2, right? Now, I want to know what is the difference or the distance of x from its own centroid. So this cluster has a centroid here. This is mu1. This cluster has its own centroid, mu2, right? I want to know what is the difference between x and its own centroid. How can I compute that? Well, I don't know what is this cluster of x, right? Correct? So I can treat it as a random variable, right? The cluster of x is a random variable. It could be C1. What is the probability of x belonging to C1? Say this is xn. The probability of xn belonging to C1, if you look at the board, this one, sorry. Yeah. The probability of xn belonging to cluster 1 is Rn1, right? So that guy is Rn1, right? Everybody's clear? What is the chance that xn belongs to cluster 2? What is that? This is Rn and 2, right? Now, what I would say that the distance between xn and its own cluster, so this is cluster of xn, is one random variable, right? Because x could belong to cluster 1, it could belong to cluster 2, right? Correct? And if it belongs to cluster 1, then this is going to be xn minus mu1. If it belongs to cluster 2, it's going to be xn minus mu2, right? Now, what if I want to compute the expectation of this guy? Can you help me doing that? What are the possible outcomes? The first outcome is that xn belongs to cluster 1, right? What is the chance of that one happening? Rn1, right? So I'm going to write this down as xn, when it belongs to cluster 1, so instead of cluster 1, I should write it down mu1, right? Correct? If it belongs to here, cluster 2, I need to write down here mu2, right? Correct? Now, what is the chance of this guy happening? Rn1. What is the chance of this guy happening? Rn2, right? That term is the same term, right? Everybody see it? If I sum it up over k, this guy, I am basically computing the expectation of xn from its own centroid. Because I do not think anymore that xn necessarily belongs to cluster 1 or 2. I would say it could belong to cluster 1, it could belong to cluster 2. And each of them is happening with one specific probability, right? Sorry. Okay. So what I can say that what I am computing here is the expectation, the expected difference of every single point from its own centroid, right? And this is basically what we tried hard to initially formulate by defining that particular risk, right? Now, what you are doing actually, you are defining an objective function, and this objective function is simply telling you how bad your algorithm is working, right? Because for every single x, you would say, I am going to find the difference between x. If you randomly give me one x, I want to know what is the distance of that x from its own centroid or its own cluster. And then if I want to know what is this guy in average, I need to just average it over all possible points n, and over all possible cluster with the coefficients that I have here, right? Now, you can go ahead again, solve this problem, but this time, instead of solving it for r belonging to 0 or 1, you just solve it for any real valued r, which is between 0 and 1, and it adds up to 1 when you add it up over a cluster, right? So same optimization problem, but your variable is being a bit different, okay? And this is a better problem, is well-defined problem, so it's going to give you a more robust solution as compared to the one you got by k-means clustering. Okay? Everybody's clear? Questions? No question? Okay, cool. So if you got no questions, so just this is a kind of like final algorithm that you're going to get if you solve that problem. If you solve that problem, you need to, again, to just solve it by alternating optimization. But this time, every single optimization is more straightforward to solve, right? And then the thing that is the main difference here is that the r that you are going to find is going to be something of this form, okay? Now, look at this term. Let me just make it a bit larger so I don't know why, but okay, look at this term here, okay? This is e to power something, right? You don't care about this beta. This beta comes out of your optimization problem. You can find it. But look at this term. So first of all, this exponential term, can it be zero? Can it be negative, sorry? No, it's always positive, right? Now, you have e to power xn, so x, its distance from the centroid of all the clusters, right? Now you want to see what is the probability of x belonging to cluster k. You just take the distance to cluster k, you normalize it by this expression when you add it up over all the clusters, right? Everybody's clear? So it's again, basically, you look at this guy, you just see what is the distance from everybody else, right? You put it inside this expression, you are just normalizing the distances in a nonlinear form, right? And at the end of the day, the one which is closer is going to have higher probability, the one which is far away going to have less probability, right? Everybody's clear? So if mu k is very close to xn, basically if it is exactly xn, then this term is going to be 0, the denominator is going to be 1, right? And anyone else which has any other mu which has more distance, this is going to give you an expression which is smaller than 1, right? And this means that the one which is closer is going to have higher probability. This makes sense again, right? But this time you are not restricting yourself to just assign it specifically. You give this level of confusion to yourself. That, okay, I think this belongs to this cluster which has the closest centroid, but there is also a tiny chance that it belongs to other clusters as well, right? And you take it into account. Everybody's cool? Questions? Now, you obviously see that if I sum it up over k, the numerator and denominator are going to cancel out, right? Everybody sees that, right? If I sum this term over k, then denominator is summation of this exponential term over k. Denominator is summation of the same exponential term over k. This is 1, right? If it was not 1, then I had done a mistake in my solution, right? So, everybody's cool? Now, one tiny question, and I don't expect you to answer it right now, but seeing e to power some quadratic term, does it remind you of some specific distribution? What is it? It's a Gaussian distribution, right? And if you look at this Gaussian distribution, what is the mean value? Just look at one term. I do know this is not exactly the Gaussian distribution, but it is related to that one. Can you tell me what is the mean value? The mean value is mu, right? Yeah. And what about the variance? It's a multi-dimensional, multivariate random variable, right? What is the covariance matrix? It should be identity, right? If it was not identity, then you have the covariance matrix inverse in the term, right? You don't have it, this is identity, right? And this is what K-means clustering is assuming, actually. Okay, but more about that next week. Okay, then the centroid update is going to be exactly the same thing as before. So basically the only thing that changes is the assignment calculation, which is going to be now more smooth. Now you're going to see better performance or better behavior, more realistic behavior when you do the clustering by this algorithm. This is what we call it soft K-means clustering. So if you want to know more about that, you can check Mackay's textbook, but basically the algorithm is this one. I mean, there's nothing more algorithmically into it, but if you want to just see more interpretation, you can check that one out. Okay, questions? No question? Okay, just the last thing before we finish this session. So as I told you a couple of times, what K-means clustering is doing is somehow assuming that your data belongs to a Gaussian distribution. What does that mean? Say you have two clusters, okay? What does the K-means clustering assume without you knowing it is that it would say, okay, the data points are Gaussian distributed, are normally distributed. And they are distributed with some mean, which is the centroid of the cluster, and covariance matrix identity. Okay? It's somehow assuming that. And it would say there are, for example, two different clusters, so there are two different Gaussian distributions. One of them is located here, one of them has been located here, right? And the data that you see is coming from one of them, right? Okay? And if you find out that it's coming from this distribution, then it belongs to this cluster. If you find out that it's coming from this distribution, it's coming from this cluster. Okay? This is something that implicitly K-means clustering is assuming. And how we can find out that it's assuming that one? Well, we first need to understand what is distribution or density learning. So the next thing that we are going to discuss next week is density learning, meaning that when you have a bunch of data samples, you start to assume that these samples are coming from one distribution. Okay? And that distribution has a bunch of parameters. For example, they are coming from a Gaussian distribution, but I don't know what is the mean and variance of that distribution. Now what you do, you try to somehow develop one framework such that from those samples you can estimate the mean and variance of that distribution, right? Now if you do this, then we're going to see as a conclusion, after understanding the process of maximum likelihood, that K-means clustering, even though it was the solution of this risk minimization, but also it is the maximum likelihood estimation when you assume, you know, K distinct Gaussian distribution being added together with those coefficients R. So this is the Gaussian mixture model. So you actually somehow impose Gaussian mixture model to your data, and then depending on where it comes, which pick it's coming from, you just give it to a cluster. Yeah, but we're going to discuss it more in details next week. Everybody's clear?